starting, take over. I'd like to remind you that just after her talk, we have these flash talks again, so be prepared. And today, at 7 p.m. here, we have also the public talk by Rosalie Lopes. So it'd be very good that if you could stay, because she's already... Okay, Manuela, it's up to you.
Yes, I have this one. Thank you, Alan. Okay, so today, as I promised, we are going to talk about the halo, but I have, maybe can we turn this light off? Hi, Franz, thank you. I put a summary on the thick disk just to remind everyone what did we say yesterday. So thick disk stars have on average metallicity of minus 0.5. They are these ones here, so they are centered more or less in minus 0.5. They have an age of course, they have a spread in age, and also, as we said, we don't measure ages very precisely, but they are old, maybe around 10 gigayears or so, as the size of the symbol show. They had a rapid star formation. We know that because they are enriched in alpha element, in this case titanium. They dominate at a height above 1 kiloparsec, more or less. So that's why they're called thick disk, because they are not confined in the plane. And they become negligible outside the solar circle. So as this cartoon shows, the thick disk is here, thicker than the thin disk, but it kind of disappears outside the solar circle. This is what we saw yesterday. I put here, in case you want really a number, as a reference, the scale length, the vertical scale length of the thin disk, which is 300 parsec more or less, and the vertical scale length of the thick disk, which is about 1 kiloparsec, and the radial scale length of the thin disk and of the thick disk. And as you see, the thick disk has a higher vertical scale length, but a smaller radial scale length. And I also want to put this also to remind myself to tell you that there is a review by Joss Blend-Hawthorne that is very, very nice. It's a review on the Milky Way. It's called The Galaxy in Context, Structural Parameter, Kinematics, and I don't remember what was the other thing. It's a very nice summary of what was known about the parameters of every galactic component in 2016. And also it's interesting because it compares integrated properties of our galaxy that sometimes are difficult to find with the similar property of external galaxies. So I recommend it. Yesterday, because it was late, or I thought it was late, I omitted this slide, but then I decided it's beautiful, and so I wanted to show it anyway, even if it's still on the thick disk. This is from a paper by David Katz et al. This year, based on the second data release of Gaia, and it shows the kinematic of the disk. The reason why I like it is that I didn't, because I didn't talk about the thin disk, and I will not, but I mentioned here that the thin disk flares up in the external part, and the thick disk kind of disappears, and you could see it very well here, in which these figures show the velocity dispersion, the radial, this one transversal in the sense of the galactic rotation, and this is the vertical velocity dispersion. So the color is the sigma. And you could see that outside the sun is at 8, is this little dot actually. You see that outside the sun, the stars with low sigma, so the stars that move have a very cold kinematics, they move in a very ordered way, flare up. So that's why we say that the thin disk flare up. I think it was very beautiful to see it like this. Pedro, the new battery is going already. It's already dead. I just bought a new battery for this thing. Never buy this thing. It kills the battery in 10 minutes. Okay, now we do move on the galactic halo. I must say that it's It's been very interesting to do the exercise to study the galactic halo a bit more in depth. To do this class, I normally work on the galactic bulge. I read the halo sometimes. I never have enough time. So now I had to take the time to read the latest paper on the halo. And I must confess that there is quite some confusion in the literature. So I will make a summary as I understood it. If there is somebody working on the halo that has a different idea, I will be happy to convert this class in a discussion. Okay, so before Gaia, in particular around 2010, we started to get the idea that the halo had a dual nature. Thanks to the work by Nissen and Schuster and by Carollo and collaborator that we will talk about very soon. Do you remember the Tombre diagram that helped us to kinematically select distinct population in the Milky Way? Yesterday we studied the thick disk. Do you remember the thin disk is made by stars that move like the sun, so they are close to 0, 0 in this plot. The thick disk has less rotation than the sun, but much higher transverse velocity. This was the thick disk, and this is normally selected as the halo. A very common selection of halo stars is stars that have total velocity, so the quadratic sum of all these things, higher than 200 kilometers per second. So these were halo stars, and Nissen and Schuster for the first time proposed that all the halo stars actually could be separated in two populations according to their alpha over iron ratio. So this is alpha over iron, where alpha is the combination of different elements, and this is only magnesium, which is one alpha element. So these guys show that the distribution of halo stars in this plot could be separated in two sequences, a high alpha sequence and a low alpha sequence here. If you, of course, combine the measurement of different elements, you can reduce the spread, so we see the two sequences much better here. The crosses are the thick disk for reference. And if you then plot the stars that you could separate here, you plot them there, you would see that the high alpha stars are more in prograde orbits. Prograde will be everything that is less than 230 more or less in rotation velocity, while the low alpha stars are more in retrograde orbit. So they proposed that maybe the blue stars were the inner halo, and they were formed in situ perhaps because they almost have no rotation, but the little rotation they have is like the rest of the galaxy. Instead, the outer halo, which is in red here, has low alpha, so was formed with a slower star formation compared to the other. So really had a different star formation, so it's a different component, and they have more retrograde orbit. So perhaps this second one, the low alpha sequence, was an accreted component in the halo. Daniela Carollo further developed this idea, and actually I don't know why I repeated this. I think I should have only plotted that. This is a bit complicated. I hope to be slow enough. Daniela Carollo examined, I go back again, examined data from the Sloan Digital Sky Survey within 4 kiloparsec. She found that the yellow has a metallicity gradient. Let us examine this plot before. So height from the galactic plane go from small 8 up there, it's dead, to high rate at the bottom. If anybody has a pointer, I would be happy to change this. And so the arrows, you see that there are arrows in here. These arrows mark the mean metallicity of the thick disk, and another component that she called the metal poor thick disk. Is not clear if this component really exists or not, but we will not talk anymore about the thick disk in this class, so I only selected the the vertical height regions in which we have only inner halo and outer halo. So she said that between 6 and 7 kiloparsec of height from the plane, we are dominated, the halo is dominated by a component that is relatively metal poor. The mean metallicity marked by this arrow here, the second from the left, it's minus 1.6. You see the distribution more or less. Thank you. So, more or less. It's me. I kill the battery as soon as I take it in my hand. Okay, so the distribution is centered on minus 0.6 in here, but when we move forward, so when we move to higher and higher height from the plane, above and below, of course, the metallicity distribution becomes more metal poor until reaching minus 2.2 more or less, and this will be the outer halo. She plots here, as a function of Z max, the fraction of inner halo and outer halo. So we can see that in the inside of the, closer to the plane, we are dominated by the inner halo, and up in the much higher, we are dominated by the outer halo. So far, we might take for granted that there are these two components. They have different mean metallicity, and according to Nisser and Schuster, they have another one. I'm going to kill this one as well. According to Nisser and Schuster, they also have different kinematics. Remember the Tombre diagram? And different alpha over iron ratio. So, give me just 1 second. Huh? If I can do this properly. Not needed anymore. Oh. Okay. So now that we have Gaia data, we can construct the Tombre diagram from Gaia. So as you see, we can populate this diagram with many more stars. Remember that we needed Gaia because we don't really measure the transverse velocity. We only measure proper motions. If we want to convert transverse velocity into proper motion into transverse velocity, then we need to know the distance quite accurately. So in this new version, this data version of the plot, this is rotation velocity. It is not centered on the local standard of rest. The local standard of rest will be here. So here is not 0 as it was before. It's the same. It's just that where there is the higher concentration of stars, actually where there is the white cross, there is the sun. So one of the most interesting things that we can learn with the Gaia data now, is that we can make a color magnitude diagram of the components selected in this plot. In principle, you would like to select the component as we were doing before, no? For the total, according to their total velocity in the galaxy. So maybe you would like to make the selection. I'm sorry, this is confusing. Okay, maybe you would like to select the stars like the thin disk in this region and the halo in this region. However, in order to do that, in order to select on the total velocity, you will need to have also the radial velocity of the stars. And Gaia, which is a photometric satellite, does not measure radial velocity by itself. There is a large group of stars for which radial velocity were measured separately, but is smaller than the total sample. So if they want to make a selection on the total velocity, so according to circles in here, they have a much smaller sample of stars. I will show the selection later anyway, because you can see that we see the same structure, just based on a smaller number of stars. So using the whole number of stars, they made a selection only on the transverse velocity. So they selected thin disk with stars located only here. We will not talk about that. Thick disk stars in this range. And halo stars with transverse velocity higher than 200. So this is the color magnitude diagram of the thin disk. This is the color magnitude diagram of the thick disk, and this is the color magnitude diagram of the halo. Let us look at them a little bit. So we see, of course, the main sequence very well populated in all three, and the red giant branch very well populated in all three. In the thin disk, we see that the main sequence extends to brighter magnitude. Of course, this is not surprising because this is a younger population. So we have massive stars still alive up here. In the thick disk, you see those stars disappeared because we don't have anymore many young stars in the thick disk. We have kind of a single turn-off, more or less, in the thick disk. Instead, here we had a larger spread. This is also an indication of the fact that here we might have a larger age spread than the age spread we have here. But when we move in the halo, the very surprising thing is that we see a double sequence everywhere, in the main sequence, in the turn-off, and in the red giant branch. So this was kind of shocking because people did not expect that in here there were two populations so clearly separated in the color magnitude diagram. I mentioned before that this is probably not the best selection for halo stars. They also made a selection of halo stars with total velocity above 200 kilometers. This is the standard selection that other people did before for halo stars, but they are left with much less stars. They are left with much less stars, but you can see very clearly that they still have, of course, the diagram will not be this. It will be a diagram with much less stars, but they don't publish it, so I don't have it. But still, you can see the two sequences. So what I want to stress here is that the actual selection here is not critical to make these two sequences disappear. So a very nice interpretation of these two sequences that I found in the literature is this paper by Gaillard et al., 2018. I don't know what's the status of this paper. It was submitted to Nature many months ago. I think it didn't go through, but it is on AstroPH. I guess they submitted elsewhere. This is what I heard. But the paper is available, and I don't know how does it go with the referee, but I think that this analysis is very solid, convincing. Let us look at it together. These are the two observed CMDs, the same we were looking at 1 moment ago. This is the thick disk. You remember it had some young stars, not many, and only one turn-off. And this is the halo CMD with two clear sequences in the turn-off and above. So Karma Gaillard and collaborator is an expert, a world expert in reproducing observed CMDs with synthetic stellar population. So if one thing she knows how to do well is this. That's why I'm showing a few of you that know her, know what I'm talking about. That's why I'm showing this paper, even if it is not accepted to a journal yet. And in fact, you can see that the synthetic populations resemble really extremely well to the observed population. This is the halo, and this is the halo. You see, she can match very well the two sequences, the two red giant branch, in the observed CMD. And so what she found is that she can reproduce these sequences under the following assumption: that the two halo populations, the red and the blue, have the same age distribution, very old age, with a peak at 12.5 maybe, and dropping abruptly above 10, so nothing older than 10. Remember that here we don't really have a lot of age resolution, so older than 10 is like more or less the same thing, like almost a single stellar population. But the important part is that she finds that the two sequences have the same age And the reason why they are split in color is because they have a different metallicity. This is the metallicity distribution of the population. This is the blue, like this. This is the synthetic, and this is the blue sequence and the red sequences. And here they compare the population she needs in order to reproduce the color magnitude diagram with the known metallicity distribution of these stars as measured by apogee. So for the metallicity, she is not assuming wild things. She is taking what is observed, and for both population and actually also for the thick disk, more or less, pretty close. So the black histogram is the distribution that she needs in order to reproduce the thick disk. So these agree with the observations, and in the age plane, this is the thick disk. So, in other words, what she's finding is that in the halo, there are two populations with the same age, but two different metallicities, and they are both older than the thick disk. This is important for what we will see later, because according to other studies, maybe the red population of the halo could be associated with the thick disk. And according to Karma Gaillard and collaborator, this is not. So these two populations are separated. In the halo, they are both older than the thick disk. Okay, let's put this information on a side, let's keep it, and move to another analysis of halo stars made by Hayes et al. They combine the information from Gaia with the information from apogee. So this is the plot. Of course, apogee is a big spectroscopic survey of many stars in the near infrared, so the main product of the apogee survey is abundances. So what he analyzes the magnesium over iron trend versus iron. You remember, we saw this yesterday. We had the thick disk and the thin disk. Now there is a new population, and maybe there is also this other new population. So tentatively, these guys make a cut. They call halo stars anything that is more metal poor than minus 0.9 in metallicity. And they see that if they cut in this way, this region of the diagram is populated by two groups of stars, one high alpha and another low alpha group of stars. Now I'm going to overlap to this one the plot we were seeing before by Nissen and Schuster. So you can see that these two populations in red and in blue coincide pretty well with the population. You can see, I hope you can see the transparency. These are the stars by Nissen and Schuster that overlap pretty well the low alpha sequence that we are analyzing now, and the blue ones overlap pretty well with the same limits here, the high alpha. So if they really trace the same population, we know also that their kinematics is different. Their total velocity of the red stars, the low alpha stars, is the total velocity is higher, and they are on preferentially retrograde orbit, according to Nissen and Schuster. What Hayes et al. Do is they compare the magnesium over iron abundance with that of satellite galaxies in the Milky Way. Most of the satellite galaxies have very low alpha, meaning that they formed their stars slower than any other population in the Milky Way. And this is not surprising, because they are, in the universe, they are much lower, much smaller over densities. So it is consistent with cosmological model that the much smaller over density contract slower and also formed stars slower. So this, none of the two components is compatible with the element ratio, magnesium over iron ratio, that is found on dwarf galaxies. However, if instead of a typical dwarf galaxy, you take the Large Magellanic Cloud, which is an especially massive dwarf satellite, you see that there is some overlap between the magnesium over iron, of the Large Magellanic Cloud and that of the low magnesium halo. So with this interpretation, they conclude that perhaps the low magnesium sequence is an accreted component that might have come from the merging in our galaxy of satellites of the same mass or perhaps more massive than the Large Magellanic Cloud. So basically, their interpretation will be that these stars could be accreted also because they have, on average, more retrograde orbits, while this one could be in situ. They might be associated to that. However, it must be said that they really look like the low metallicity tail of the thick disk. We don't really see a break there. If somebody told us that this is just the tail of this population, I think we would believe it, right? So the same authors say we are not sure that we are seeing an in situ population. Maybe we are just seeing the low metallicity tail of the thick disk. So one of the conclusions of this paper is that maybe there is no such thing as in situ halo. They also examine the kinematics, given that they have Gaia, and they say that the low magnesium sequence has no rotation. This is velocity with respect to the, I think this is the galactocentric standard of rest, as a function of longitude. So when there is no rotation, this thing is flat. Instead, when there is rotation, this is the high magnesium, the supposed in situ component, or maybe thick disk, that has a rotation. You see there is a kind of a sinus in here. So they say, this is compatible with the fact that this is maybe an in situ halo that is rotating, but also does not allow us to conclude that this is different from the thick disk. Because it is rotating, it is compatible in terms of abundances with the thick disk. So for us, this is most likely the thick disk. And this is why it was important to remember the paper by Gaillard. Because Gaillard said, yes, we have two halo. In the color magnitude diagram, we have two sequences, but none of them is compatible with the thick disk, because they are both older than the thick disk. So maybe we are seeing the older tail, the older and more metal-poor tail of the thick disk. Maybe not. According to Gaillard, let me go back 1 second, if I can. Sorry if I go fast. According to Gaillard, there was kind of a gap between the age of the halo and the age of the thick disk. But I honestly don't know how much we can believe to this gap. So at the moment, I think we are left with these two possibilities. Maybe there is an in situ component, or maybe that's just the thick disk. But for sure, there is an accreted component. On this, everyone agrees. And actually, Amina Elmi and collaborator came out with a Nature paper last year, or almost 1 year ago, in which they demonstrate, or at least they argue, that most of the halo, which is the component we were looking at before, the accreted component, is indeed accreted. It is the result of the merging of a huge satellite that they tentatively call Enceladus. They decide that because this is the Thornbury diagram made for all the yellow stars. Well, sorry, this is the Thornbury diagram that we were seeing before. So the sun will be here at 220 and 0. Here there is the thin disk, here there is the thick disk, and this part will be the yellow. She colored the plot in blue according to a selection in another plane that is not shown here, according to a selection on the angular momentum and energy. I will say something about this plane in a few slides, but it's almost equivalent to select high velocity stars in there. And she makes a simulation of the merging of a huge satellite with our own galaxy, and she finds that the distribution of the debris, so of the stars that have been accreted from the satellite, resemble very well these stars, and also has this strange thing, you see, that is present there. Also, the simulated, okay, these are not the simulated, I'm sorry. She shows the observed stars in this plot. They will be the one that resemble the accreted satellite would distribute like that in the alpha over iron plot, just similar to what we were looking at, and they will populate the blue sequence in this plot. You can barely see it, but there is another one that is a red sequence that is either the in situ or the thick disk, but the blue one would be very well explained by the huge satellite impacting our galaxy. She estimates the mass that the satellite needs to have in order to sustain for 2 gigayears the star formation rate that is required by this plot. As I told you yesterday, this plot is a constraint on the star formation rate, right? The higher the alpha over iron, the higher the star formation rate that the population underwent. And so in order to explain that, she needs a star formation rate of 0.3 solar masses per year for 2 gigayears. So more or less, the total mass of the satellite would be that. This is more massive than the Small Magellanic Cloud, about 2 Small Magellanic Cloud, a little bit less massive than a Large Magellanic Cloud. I should tell you that there is another paper by Bland-Outward that give a much higher estimate for this mass. But apparently nowadays, everyone agrees that this component, the accreted part of the halo, is really the result of the massive merger. This is consistent with the fact that the impact of this massive merger about between 8 and 11 gigayears ago will be the merger that created the thick disk. So in that moment, the disk that was in place, that was thin, thickened due to the perturbation, to say an euphemism, of this satellite falling in. It thickened, so the rest of the star formation in the disk built a new thin disk. And this is why the thick disk doesn't have stars younger than that, because it grew up, what was already converted in stars was heated, so was increased this vertical height from the plane, and the new star formation happened again in the plane. So we don't find stars younger than that in the thick disk. The distribution in the sky of these accreted stars, according to Amina Helmi, would not be uniform. This is the position where most of the stars belonging to this Encelado debris would be in the sky. I didn't mention it, but there are evidences also that near the sun, the velocities of the disk, the position of disk stars in the phase space is not uniform. There are clear signs of perturbations. It is now called the corrugated disk, which are consistent with the fact that there might have been this massive merging event. So this is, I think, everything we know for the moment about this massive merger, but we have been knowing for many years already that in the halo there are traces, clear traces of many more recent accretion events. These are the so-called streams in the halo. This is a famous picture of the field of streams as observed in a density plot from the SDSS survey. So this is a huge field in the sky, in the northern sky, in which you can see clear streams, these two tails of the Sagittarian stream, the Orphan stream, Monocero ring, etc. These are globular clusters or dwarf satellite. Normally, these streams have very, very low density in the sky. So you would not actually look at the star, make a map of the number of stars, star counts, and see this. You will not. In order to see that, you have to choose special tracers that are defined in the color magnitude diagram in such a way that could actually trace streams. What would that be? Because we know that the satellites, the satellite galaxies that are close to the Milky Way in this moment are all dwarf spheroidals, which are old and metal-poor galaxies. We should find places in the color magnitude diagram where only old and metal-poor stars would go. And so if we select those and we map those stars, we plot those stars in the sky, then we do see overdensities. This field in particular was constructed by selecting stars on the blue side of the turn-off, where indeed there are a lot of stars, so you could make a map with a reasonable signal to noise, but the most metal-rich stars would miss this box because they would evolve like that. So by selecting stars in there, you obtain this. Another way to trace streams that there are many actually, blue horizontal branch, etc. But another one that I think is worth mentioning is the use of RR Lyris. RR Lyris are pulsating variables that can only be present in population older than 10 gigayears. This is because in order for a helium burning stars to cross the instability strip where they can pulsate, you need to develop a blue horizontal branch. And you can only develop a blue horizontal branch in a population older than 10 gigayears. If you have a population that is younger than that, stars burn helium in the core always on the red side, in the red clump. So they will not cross the horizontal branch. Yes, they will not cross the instability strip. So in other words, RR Lyris are always older than 10 gigayear. And they are also metal poor on average. So they trace, as we said before, a possible dwarf satellite that fell into the Milky Way, but they also have the advantage that they yield a very precise distance. So you don't only can construct a map like this, you have the velocity of each, you have the distance of each point. So you can put the constraint that the stars have to clump also along the line of sight. By doing that, in particular, Kati Vivas and Bob Zinn had done this exercise a lot. They traced in a plot like this in which there is distance and right ascension, for instance. You see the Sagittarius stream, the Virgo overdensity, a galaxy. You can look for clumps in this plot in addition then in the sky. Another possibility that was opened now by Gaia is to look for streams in the 3D velocity plot. This is the famous Tombre diagram that we have seen a zillion of times. Koppelman and collaborators have identified several new streams based on clumps in this plot. And something that I mentioned briefly before is that you can also construct a plot in which you have energy and angular momentum in here. And you see that in this plot, here the x-axis is the same as this. In this plot, you see that the candidate streams clump very much. That's because angular momentum and energy are integral of motion, so they are conserved along the orbit. Instead, if we look at this plot, we have instantaneous velocities. We have the velocity we measure now, and they might not be representative of the orbit if the star is precisely at their apocenter or their pericenter. They are at two extreme values of the velocity that might not be representative of the whole orbit. Of course, the limitation is that in order to do that, to put here an energy, you need to sum the kinetic energy and the potential energy. And in order to know the potential energy, you have to assume a shape for the galactic potential. You might make a reasonable assumption. I guess these guys, for instance, made a reasonable assumption, otherwise this thing would not clump. But of course, you have to build the model a bit more complicated than that, which is almost just observations. So Gaia opened up a new possibility also to look for new streams unknown before. And of course, we know that there are these kind of streams everywhere in the universe. We see beautiful streams around other spiral galaxies. We now know about similar streams even in Andromeda, so it is not at all surprising. But as I was mentioning to Denise, I think a few days ago, I just want to, I think it's important to keep in mind that these kind of streams made up make up a very small percentage of our galaxy. So of course they are there, of course they are important, but it will be really a huge jump to conclude our galaxy formed by accretions, because the sign that we have of accretion, which is indebatable, it's clear, makes up a small percentage. Even if it is true that Enceladus came in and is a huge satellite that might have built up a major fraction of our halo, a major fraction of our halo is still a major fraction of 1% of our galaxy. So, right? No. Okay. Now I have a summary on the halo field stars. And here is where I try to summarize, it's tough to summarize. So maybe we can discuss here. Before Gaia, we had a view of the halo. I'm talking about field stars, without globular clusters, without individual streams. Typical halo stars as having a dual nature, no? An inner halo, oh, I should have said here also Nisser and Schuster. There is another reference that I forgot. An inner halo and an outer halo. So the inner halo would dominate within 15 kiloparsec, would be relatively metal-rich, around minus 1.6, would be non-rotating, and it was interpreted tentatively as an in situ component. The outer halo would dominate further than 15 kiloparsec from the galactic center. It would be more metal poor on average, around minus 2.2. It would be retrograde, and it was tentatively interpreted as an accreted component. I want to keep in mind that when, in particular, Daniela Garolo and collaborator, I'm citing this one because it was a very important paper. The first paper came out on Nature and was a big revolution. They proposed the presence of an inner halo and an outer halo separated at 15 kiloparsec, but they only analyzed a sample of stars around 4 kiloparsec from the sun. So how did they know? Because they reconstructed the orbit from the instantaneous velocity, so which is good to do, but you have to keep in mind that it's an indirect inference. It's not that they measured these stars outside 15 kiloparsec. They were anyway only studying stars relatively near the sun. After Gaia, this is even worse. Now we are studying, for the moment, only stars within 2 kiloparsec from the sun. The picture changes a little bit because all these authors propose that there is a high alpha halo and a low alpha halo. So the high alpha halo is non-rotating, you remember? It is rotating. The high alpha halo is the thing that resembles the thick disk. So it is rotating. It is more metal-rich. It's minus 1.6. It is the red sequence in the color magnitude diagram, and it has been proposed as the in situ component. While the low alpha halo is non-rotating, according to this guy, we saw the plot. Their mean metallicity is around minus 1.5 from Gaillard. It makes the blue sequence in the color magnitude diagram, and it might be accreted because the alpha element is consistent with the large Magellanic Cloud. So now nobody is talking anymore about inner halo and outer halo, but I think that this is the same thing, no? Because it is not rotating, metallicity is consistent, it is bluer, and it is compatible with being this Encelado thing. This, I think, is the thick disk. Because we also, as we summarized yesterday, the mean metallicity of the thick disk is this. It is rotating because it is metal-rich, is the red sequence, and we think it formed within our galaxy. I think this is the thick disk. The only possible inconsistent is the fact that Gaillard says that this component is older than the thick disk. But with the precision we have, maybe, I don't know. And this I don't know. Maybe after Gaia nobody is really seeing this because we are limited at here, and so this is just not appearing. This will be the best summary I could do on the halo, honestly. And I finish with the halo. I not necessarily need to finish my class, but I would open debate. In here, Alan is sticking a finger. Tell me.
So Nielsen issues the paper. The results they are here, no? In this, the metallicity minus 0.6 and minus 1.5, if I remember.
Yes.
So do you think that?
They cannot give me a metallicity because they have few stars. But it's true that they have a sequence with high alpha and low alpha.
So do you think that part of the Nielsen just a sample belongs to the thick disk, for instance?
I think because look, actually they say something like this. I don't remember exactly what they say, but they show the plot. And I have the plot. Let me find it. Where is it? I put the real plot instead of the transparent plot. Actually, why don't I do this? Should do this. It's more didactic. Read my email, please.
I want to see the details.
No, just take away. Where is the plot? Oh, I have the paper here. Where is the paper? Doesn't. And if I do this, maybe I do full screen and you have it. No, I have it. I will make it, don't worry. Give me 2 seconds. Meanwhile, you can think. View, full screen. Hey, it goes away. It goes away when I do full screen. Why? View, full screen. But you cannot see maybe. Okay, this was a bad idea. Okay, let's forget about. Here, just like that. You see, this is the blue halo, and this is the thick disk. The crosses are the thick disk. Of course, he has less stars. You see, this is the thick disk.
But the other two populations are the inner halo and outer halo, no?
Yeah,
The interpretation.
this is inner halo and this is outer halo. And you see that the inner halo, in fact, seems the thick. In fact, seems the thick disk. So then, if this is true, if the she doesn't quite say inner halo and outer halo. She says in situ halo and accreted halo. But of course, this should be more inner.
Inner.
So then, what I summarized is not quite. Where is my point? Lost the pointer. Coming up. Yeah, I was there. So, according to Nisser and Schuster, it was the high alpha halo. Yeah, the high alpha halo was the thick disk. It's okay. What is not consistent is the fact that they found that this was the inner halo. I think at the moment we have a little bit of a confusion in the literature. There is another thing that I would like to stress.
And
yeah,
I don't know, I got lost with the idea that these Encelados, I think that you said that Encelados would create in that big merger, would create the thick disk.
Yes, no.
Or part of it.
No. The Encelado became the accreted component of the halo, but because of the shock, the disk that was in place became thicker. Became the thick disk, but not because it was made of stars from Encelado.
So nothing of the thick disk was accreted in this way?
No. So, it's just that it changed its shapes. It is clear for everyone because maybe I was confusing. When I said that this accretion event created the thick disk, I didn't mean that stars in the thick disk can be accreted. I just meant that because of the perturbation, what was a thin disk heated up, but still made of stars in the disk. what I wanted to say is that I've been reading many papers from the year 2 of Gaia. They were published almost simultaneously. Now you have seen that within 1 week there were many papers about the year 2. The most interesting ones for me were the one by Babusio with the color magnitude diagram, so you could study the age distribution of the cellular population. This one by Hayes that combined Gaia with Apogee, and another one by David Katz who analyzed the kinematics. But because they were, I guess they had agreed to lead each one a paper, in the paper with the color magnitude diagram, there is no plot of the kinematics and of the abundances. And if you take the paper of the kinematics, you don't see not even a single color magnitude diagram. And if you take the paper with abundances, there is no ombre diagram. You see? And so it's really quite confusing. I think this is a problem. This is a bad spot in time that we chose for that, because at some point there was some kind of embargo in the paper that needed to be led by another collaborator, but right now that papers are out and it's 1 year later, I think now we will start to see paper with a more heuristic analysis of all the data, because at the moment it was really painful to see. We made a selection based on kinematics, as for the plotting cuts, and then there is no, it's not. Well, I did the effort. But anyway, as I said before, I realized that I'm living with a confused picture, because it's confusing also for me. I think it is confusing in the literature, but in this moment. But I hope that we now have the tools to be able to read another paper that comes on the topic. The most important thing for me, as a goal of this class, is not to give you the result. The inner halo has been accreted and that's it, because this result can change in 6 months. What I would like to convey is more the tools to study these populations, so you would be able to read all the papers that come out and hopefully clarify the pictures. We have some time, right? I can go to my favorite bulge. Or if I have questions.
I would not completely discard the idea of the outer halo, because most of the studies that put the outer halo as a reality are talking about the streams. And even if you compare the range of distances for the two situations before and after Gaia, the outer halo would have a metallicity very smaller than the other components that you have shown after Gaia. And the age where you shown that the outer halo would be dominant would be the distance, in fact, would be after 9 kiloparsec from the sun.
Thank you for this question, because it allows me to clarify something. When I said this, I didn't mean, maybe I said it at some point without thinking too much. I didn't mean that we don't have an outer halo. I think that this component is possibly not mentioned because we are at the moment limited to a region, to the analysis of the region very close to the sun. So the two components that people are seeing in this data are most likely, in my opinion, the thick disk and the inner halo. And they are not seeing this, not because it doesn't exist, but because they don't go far enough to see it. After all, it is a population that is supposed to be dominant outside 20 kiloparsec. If you are studying the yellow within 2, it is reasonable that we don't see much of it. So.
I have some more comments.
Yeah.
The idea of several components in the halo is not new. In fact, I did a review for a symposium, a IAU symposium in 2009, and I remember a paper by Morrison talking about the innermost halo. It was inner than the inner halo. And another paper by Rosie Wise saying that she found kinematical trace of the satellite that created the thick disks. There are several ideas that now we see them emerging again.
The idea that the thick disk was created by some major merging was clear for a long time, but I think we now have more proofs that might be the case.
But what caught my attention was the CMD from the thick disk. And you show that there are several stars that are younger than the turnoff. Does the paper have some information or hypothesis about them?
Look, this is interesting. Thank you for that. This paper doesn't comment much on these stars because it is a paper that was written for Nature. It is relatively short. Hopefully, they publish a longer version of it. This paper only published this. I guess that the tail will be this, but they don't comment too much on that. However, the selection they make is the same as the one in Babusio. And the selection is Babusio, let us remember, that is not ideal for the thick disk because it's written there, so I didn't forget. Panel B, transverse velocity between 60 and 150. Transverse velocity is this, so they are selecting stars in there. They say it's not the ideal because here they are plunging within the thin disk. However, they can do a selection on the total VTOT, on the total velocity, so only for the subsample that has radial velocities as well. And here, they select the thick disk as between 70 and 150 and 180, and it's like that. Actually, also has some of this. But keep in mind that this plot is a plot that I put. This is a plot from the paper by Katz. This is what I was mentioning. Babusio doesn't have a single Tombre diagram. So when they say VTOT higher, this is the yellow for instance, VTOT higher than 200, where would the 200 be? I tentatively draw it there because I think that VTOT should be centered on the sun. And so this will be 100 and this will be 200, and so this will be the halo. But I'm not sure. It could be there. Would make maybe more sense. Well, in the other side as well. Yeah, sure. Sorry, I got it here by mistake. So I'm not sure where is the 200 as she mentions, because she mentioned a selection without a single diagram. If you want to know about the velocity, you have to take the other paper. So I think at the moment there is this confusion in the literature, and I hope it will be solved.
I remember that after the Carollo's paper, remember that was the discussion. There was
a discussion about the distances.
No, exactly. So now it's a consensus that you have two populations, no, after Gaia.
I'm not sure if we are talking about the same discussion. There was Ralph Schonrich that said that there were not two populations because they had miscalculated the distances. But that's why I'm citing also the paper by Beers. There is a paper by Beers a few months after, in which he answered to Schonrich and says that actually they calculated the distance right, and there is a mistake in the paper by Schonrich. Well, whatever, where is it? Here. This is the first paper. Actually, the first paper is a Nature paper, pretty short. And then this is the second one that is on APJ, is much longer. And then there is the paper by Schonrich saying you calculated the distance wrong. And then there is this answer, a very long paper, explaining why the distances were right, and there is a mistake in the paper by Schonrich. So I distillated this. What time is it? 10 minutes. Okay. Let's say something. If we repeat it tomorrow, it's always better. One thing that I wanted to mention is that I do not have time to talk about globular clusters because there will be a whole 4 classes about where do we think that globular clusters formed, etc. And they have a huge business about multiple stellar populations. I decided to leave that aside. But I just want to mention that in the paper by Babusio, there are the color magnitude diagram of 14 globular clusters that are, in my opinion, beautiful. Here they are color-coded by metallicity. So we also see that as we expect, the most metal-rich ones are on this side, more metal-poor ones, the other are on this other side. Metal-rich ones do not develop a blue horizontal branch, while metal-poor ones do. Only to look at this picture, you can give a whole class of a stellar evolution course. I suggest you to go and look at it, but we will not talk about globular cluster in this week. I'm sorry. So next class, and please, Alan, stop me when I'm finished, because if I start talking about the bulge, I can go forever. So I just start because maybe the introduction is important. When we will talk here about the galactic bulge, we will talk about the component that is included within a radius of 2 kiloparsec. So we are not talking about, the selection is special. We are not talking about a specific kinematic population or age-selected population. It's just that region of space that we will call bulge. And it's important from one point of view because it makes a lot of the Milky Way stellar mass, 1/4 at least, maybe 1/3, depending on which reference you use for the total mass. By the way, Elio, the total mass of each component, it's written in the review by Blunt Hawthorne that it's mentioned there. Another reason to study the bulge is that we really don't know how bulge form. We don't know how galaxy form, as you clearly understood so far. But in particular, bulges, we really don't know. I went in one of the outreach pages of NASA, and I found this view graph that is from 2000. And they said that we have 3 scenarios for the formation of bulges. The one of a monolithic collapse, that I think is kind of obsolete at the moment. However, it's good to keep it there because we never know if one day it becomes fashionable again. So a monolithic, you know, for the world, is a rapid collapse of a cloud that forms a ball with a ring around it, just like Saturn or any planetary system. The most modern view of how bulge form, driven by a review by Kormendy and Kennicott in 2004, is that we have in the local universe 2 kinds of bulges: the classical bulges and the pseudo-bulges. The classical bulges will be formed by merger of small satellites. So basically, you can think about the classical bulge as a small elliptical galaxies that accidentally sits in the middle of spiral galaxies. When small satellites come in, they form this spheroidal structure in the middle. In this scenario, the merging is dissipationless. It means that basically stars already made come in. There is not a lot of gas and a lot of new star formation, kind of a dry merger. The other channel is the formation of pseudo-bulges. This is the formation basically of those bulges that looks more like a bar. They are more elongated. And we know that bars form via dynamical instability of the disk. So when you have a disk and any small perturbation in the disk naturally form spiral arms, we see this in any kind of simulation, the mere presence of spiral arms drive material in the center in the shape of a bar. And so Kormendy and Kennicott, because they saw that in the local universe they could classify bulges according to shape and kinematic properties in 2 groups, they proposed these 2 groups for the formation of bulges. I want to stress that in both cases, here there is the word dissipationless, which means that in both cases you are putting in the center of a galaxy stars that were formed elsewhere. In this case, the stars were formed in small subunits, small satellite galaxies, and in this case, the stars were formed in the disk, and then through the dynamical instability, they would fall in the center. However, this is a scenario that is driven by the property of local bulges already formed. And it is in contrast with the scenario that we see at high redshift. There are many studies of the formation of bulges at high redshift. I just picked up one. People who study in the high redshift universe are reaching a consensus around this. For instance, in this paper by Tagaki et al., they are studying bulge-forming galaxy with an extended rotating disk, so kind of proto-Milky Way galaxies at Z2. Z2, redshift 2, corresponds more or less to 10 gigayear. So this will be the moment in which a galaxy like our own formed most of the stars. Okay? They observed this galaxy in the rest frame UV, in the rest frame optical, and actually these I think were archive images, and the new images is ALMA, the high resolution channel and the low resolution channel. Basically, the paper explains at length why this channel of ALMA is tracing star formation. Basically, they are measuring emission from the dust that can only be there when there is star formation. And their conclusion is that in the center of the galaxy, they have high star formation rate surface density within 1 kiloparsec from the center, which means that they have an intense starburst that can rapidly build up a central bulge. What does this mean? That when they observe galaxy like the Milky Way, when they were baby, they had a starburst in the center, meaning they were forming stars in the center. But we think from this thing that either you form stars in the satellite and then you put them in, or you form stars in the disk and then you draw them in. So in none of them, you are having a strong starburst in the center. So we have an important disagreement in the way we interpret the local universe, where galaxies are already formed and we just study the stars, including our own, as we will see, and what people who study high redshift are finding. And this is, I think, one of the many, but possibly the most important reason to go and study the galactic bulge. This is an artistic picture of our galaxy that is made according to the data by the Spitzer satellite. Basically, this is, yes, an artistic picture, but it is a especially accurate artistic picture in which our galaxy really looks like the most recent measurements of her structure. So we know that in the center of our galaxy there is a bar. And then there are two major spiral arms and some other minor spiral arms. As I said, we will not talk about the disk. We concentrate on the fact that there is a bar in the center because there are zillions of papers that measure the bar in the center of our galaxy. And we all agree on that. I want to cite only the latest, possibly what I consider the most beautiful and accurate measurement of the shape of the inner galaxy. It is a paper by Wegg and Gerhardt in 2013. They use data from the VISTA variable in the Via Lactea survey. It is a near-infrared survey of the bulge of our galaxy and a part of the disk. It is a multi-epoch survey also, so we have variable stars. These guys use the red clump stars as a distance indicator, so to trace the density, the 3D density of the bulge. In the very center at Z0, the data were not complete enough to allow them to draw the density, but they see clearly a bar, and they also see a boxy peanut shape in the external part of the bar. This is the bar modeled by them, seeing edge on completely. They also estimate the bar inclination angle. So we see there is a bar with the peanut shape, or sometimes called an X shape. There was some debate at the beginning whether this was real or not, but I think it's now pretty proven that it's real, because from the images of the Y satellite, you could see the peanut, or the X, however you want to call it. And if you make a filter, if you subtract a spheroid component, you really are left with this. I'm sorry, no, this is not the subtraction. Sorry. This is from a paper by Atanasula, a model or bar formation. I will show you a movie in a second. So this is consistent with the way we think bar form. Just let me get to the movie, maybe. This is a new paper, always by the same people, with the same kind of data, but in which they, in addition of tracing the inner bar and the peanut, the boxy peanut, they are also tracing the long bar. Because there was some debate at some point about the possible existence of a different structure in addition to the main bar, a thinner and longer bar that might have formed by a different process, but they demonstrate here that this thin long bar, indeed it exists, but it is a part of the same structure. In fact, if you look at the paper by Atanasula, she makes a dynamical model of bar formation. When you form a bar, it is very natural that you form an X shape or a peanut shape in the central part, but you are left with the thin structure in the outer part. And if you wonder how do you form that, I have a movie. I'm telling you what happens, and then I run the movie. Basically, when you form a bar, it's natural. It forms spontaneously in many, not in all of them, but in many dynamical model of the evolution of disks. You form a bar, so you have this sausage in the middle. At some point, by some small perturbation, some bars starts bending. Now, the bars are stars, of course, in elongated orbit. What happens is that the orbit bends in this way or in the other way. So you see, as a whole, the bar that oscillates like this. It forms what I found in a paper that they are called the banana and anti-banana orbit. The concept of anti-banana impressed me a lot, so I hope you will never forget it again. The anti-banana. So you form this thing in the middle, but the external part of the bar stays the same. So this is a movie by Ruben Machado. It's available on YouTube. You have the bar evolving, and then the central part starts to heat up and to form, you see there, the banana and the anti-banana. But you also see that you have a thinner structure in the external part. See? So basically, this thing stays in the plane. So basically, we know, just to summarize a little bit, we know that our galaxy has a bar. I look at it as a bar. In the central part, this bar is thick and also has some horns. It has some. It is an X, basically, due to the fact that it has been bending and buckling for a while. And in the external part, we have a longer and thinner structure that is completely explained by models. So the 3D structure so far of our bulge is clear. And it is clear that it came from the disk, because we know that bars do not form by merging of external things or monolithic. They are the natural product of disk dynamical instabilities. Should I stop here for today, maybe? Okay.
So questions?
So I'm not sure that I understand the bar formation. It could be an evolution of the disk of the galaxy, or a collision of a dwarf galaxy, or
in our galaxy, we see that the bulge is a bar, with some caveat that I tell you tomorrow. But so far, we see that the main structure is a bar, and we know that bars form via dynamical evolution of the disk. However, other galaxies that do not have a bar, that have a spheroid in the middle, we think that this spheroid could be formed by merging of external structure. This we call classical bulge, and we think it has a merger origin. So Kormendy and Kennicutt kind of made a classification between real spheroids formed via merging. Eventually they can be 3D, but they are still spheroid, 3D, sorry. Yeah, triaxial, that's what I wanted to say. Triaxial, but they are still spheroid, and bars that have a different origin.
Evolution.
Evolution, yeah. So if it's clear, tomorrow it will not anymore. Because in real life, I think things are more complicated. But so far,
there is a 2001 paper by Allard talking about an inner bar, a second bar. Is it still on the literature?
I think it was what we were seeing, the signature of an axisymmetric structure in the center. You see, it's in the next slide, but Alan told me to stop. Tomorrow I start with that.
Here. There is some relation between those streams and the missing satellite galaxies and the small dwarf galaxies around the Milky Way?
I'm not an expert on this problem, but I think that lately the famous missing satellite problem was relaxed, was kind of solved. I think that on one side, observers found many more galaxies, the ultra-faint, etc. And on the other side, cosmologists converged in models in which they produce less zillions of galaxies. And so at the moment, I think this tension is not a problem anymore. It has been relaxed.
Other question?
As we have time, I wonder if with the new results from Gaia, so of course you are looking only at the very center of the galaxy, or very small, not center of the galaxy, very small area around the sun. Yeah. But does this impact in all the models we have, like all the ways the galaxy was formed and the different size of the structures, these kind of things that we that do not, not work with the galaxy, we use as the models for understanding different components?
I personally think that the realistic models are a few so far, like the one by Francesca Fraguti, Paola Di Matteo, Victor De Battista, because in addition of having dark matter, they also have gas and star formation, and they can predict ages, metallicity, etc. Tomorrow I will show some of these as they compare with the observations. Even before Gaia, they had some problems. They are still kind of toy models to understand the concept, but I don't know about any model that really reproduce the Milky Way. Because also these models are set in a cosmological context. So what they do is they take a cosmological simulation, they take a galaxy that ends up more or less like our own, and increase the resolution a lot on this one. They let it evolve. And this galaxy takes months to evolve, and then it may or may not end up like the Milky Way. It may form a bar that doesn't buckle, so they are left with so that's the status. I think they understood a lot because they are much more advanced with respect to previous models that either were not in a proper cosmological context or didn't have star formation, etc. But still we are in a conceptual way in a moment in which we can understand the general principle, but we cannot reproduce the galaxy and like run a chi-square to decide which one is the best scenario. We are far from that.
Other question? No? I have one. Just one, very quickly. Some people here are interested in globular clusters, no? And you just show this beautiful picture, but do you have any news about, I know that you are also work a little bit on globular clusters, so when you go to disentangle the different components of the galaxy, the halo, the bulge, the thick disk, do you have any exciting news in this sense?
No, I don't.
It's too boring.
Yeah, I haven't heard about new results that combine Gaia with personally, the latest paper I've been seeing on globular cluster are all concentrated on the problem of multiple stellar population, maybe because I read more on that side. And I haven't seen a combination with Gaia. Maybe some of them.
Okay, no other question? Last chance? No? So let's thank Manuela again. And please stay for the short talks, no? The flash one, not short, but flash.